Hello guys, good afternoon again. This is Sir GB to discuss to you some basic concepts on tensors which are very useful in understanding continuum mechanics. So this is just an introduction of how and why tensors are used to represent mathematical expressions. Okay? And the origin of tensors may be dated back to the use of explicit and vector notations. So to give you a comparison on what an explicit expression is, so we consider variables x, y, z, or x1, x2, x3 that describes vectorial notations. Okay, so we can say that these are uh, vectors defining positions uh, in space, or maybe forces directed based on the reference axis, etc. So if you are going to take a look at how the explicit notations and the vector notations uh, including the indicial notations are, you can readily see that the purpose of tensorial notations are actually made more compact, since the general language or the general uh, notations used by tensorial mechanics or continuum mechanics is the indicial notation. So when you say indicial notations, we are referring to uh, subscript, okay, as your index to determine the order or the rank of your tensor. So here you have to find explicitly or see explicitly that this vectorial notation implies a three-valued uh, quantity directed or placed in certain position. Okay, so this initial notation simply gives you an idea on the subscript I ranging. Let's say I ranging from 1 to 3 means you have two or three directional uh, variables that may be defining or describing uh, a position in space. Okay, so it can define a position or a direction in space, and the difference between the two, the advantage between indicial vector and explicit, is that indicial notations are very compact, okay, or easy to write and to annotate compared to both the vector or the Gibbs notation and the explicit notation. Of course, the vector notations are also very compact, but they are only limited to a 1 degree tensors. Okay, while tensors can be in an nth degree, can be defined uh, up to the order of n, meaning to say that the variables that may concern that are concerned to use in the mathematical computation of mechanics may be unlimited, no? Up to the nth degree. Okay, so for a matrix notation, we can see very well how compact the matrix and the indicial notations are compared to the explicit notations. You have to still write this in a very explicit manner, while you can only write it to represent the matrix A. Okay, so if you're just using uh, uh, a, a form of a manuscript to represent a matrix, a 3 by 3 matrix at that, you don't need to write everything. No? So the general idea is to make the representation of the continuum mechanics principles, solutions, formulations more compact and space saving. Okay, so for a cubic matrix, it's really a very large uh, amount of space is consumed, no? Explicitly, while in the addition notation, we can only use an epsilon ijk as a representation of this very large expression or notation. So the basic rules for addition notations are defined one by one as we go along, discussing the basic concepts. And the rule one is the definition of a range convention. So in a vectorial notation, we make use of the range of position in space, or the spatial dimension in terms of numbers like 1, 2, and 3, or x, y, z. Okay, so this is a x1, x2, x3, or an x, y, z. Okay, so while in the vectorial notation, we only have to put an x and an arrow on top. So this is now the vector notation. And the indicial notation, which is used by tensorial mechanics, is simply an x subscript I convention. So this is the rule number one for range convention. So for rule number two, the summation convention simply uses a repeated index, okay, which will mean a summation operation. So if you see there a ujj, you just iterate on j equals 1 to 3, j equals 1 to 3, and you take note that when j equals 1, this becomes u11, and then j equals 2, it becomes u22, and j equals 3 becomes u33. And since the repetition of such an index is called a dummy index, will give you an implication that we have to use a summation series of such iteration on j equals 1 to 3. So let's take an example of a scalar function. Okay, so f here is a scalar. Okay, while x is what? It's a vectorial function. So this is now a tensor, okay? A function, a tensorial function. While this is not a tensor, it's a scalar function. X is a function of z, because x is a vector, xi, then it's a vectorial function. F is a function of x, but since f is not a vector, it's a scalar function. So if we take now the total derivative or the total differential df, explicitly we have to perform these derivatives, okay? So you can write it down as the partial derivative or simply a derivative with respect to x1. Okay, so this is the vector function x1 multiplied by the x1 plus derivative of the function with respect to x2 times the x2, etc., up to point where uh, dxn here reaches its range. Okay, so this is now the range upon which your x, the vector, is defined. Okay, and we take note that this may be simply written into a summation series defining the derivative of f with respect to x i's, okay, because there are a lot of i's there, multiplied by the xi. Okay, so take a look at these i's here. So these two i's here simply refers to a repeated index, which means you are referring to a summation, okay? Summation here, or summation, okay? Or in additional manner, we can now drop the summation symbol since the repetition of the index implies that on rule number 2, this is already a summation. So we are now making the representation more and more compact, okay? And this can also be written in the initial form uh, by using what you call dummy indices. So you can use an idel, or as long as they are consistent, a jdel, and a k here. So there's no danger in compromising the indices, whatever letter you want, because there's no other index present in this particular expression. No, so that's why they are called sometimes dummy repeated indices. So note that the initial notation saves space. Okay, when you write manuscripts, when you write journals, you don't have to worry about writing all of these terms. So by simply typing this, and the reader knows what continuum mechanics, tensorial mechanics is all about, then uh, he would understand what you are supposed to send, no, as a procedural message in the manuscript. Okay, so let's have another example here. Let's expand now. The scalar function f is a function of the vector function x1, x2, x3. Okay, so x1 and x2 are vectorial functions. Okay, vectorial functions of z. Okay, so we just extended it into a more chained or nested, okay, functional, okay, a function of a function. And if we want to take the partial derivative now of f with respect to z, because z is your last variable of concern here, so df over dz1 is simply equivalent to df dx1 dx1 dz1. So this has something to do with the chain rule that you have learned from your calculus. Okay, so if we try to look at this dx1 here and the dx1 here, although they are not uh, cancelable, so you can cancel them. But if you will look into the pattern, so this is a simple df dz1, so it goes back to this original. Okay, so this is d f dz1. Of course, the context of having another, because x is a vector, you have a dx2 there, still at dz1, and so on and so forth, because x1 is a function of every variable in z. Okay, so if you are going to look into this scenario, this is now only one quantity or expression. So we still have to make use of another with respect to z2, and another with respect to z3, and another with respect to zn. So how large the explicit notation will be if you are going to present it in the form of a manuscript, in the form of a program. Okay, so better make use of a compact form, wherein df over dz, the derivative of the scalar function f with respect to z, j's, is simply equal to df dxi dzj. Okay, so take a look how to check it. So these are compatible, and this is now df dzj is simply equivalent to the left hand side of your equation. So you call now j as the free index. Okay, j is a free index, and it must appear only once in every term. It cannot appear twice here, because it will uh, not satisfy the general rule of equality. So this is now a free index there, say a repeated index here, which means a summation. Okay, so the i's there gives you now an implication that this is a summation series. And if you are going to look at the number of expression or terms, okay, the number of terms will depend on the number or the range of j. Okay, so you have one free index here. If j is 1 to 100, okay, let's say j is 1 to 100, then you have 100 equations, 100 expression, 100 terms. Okay, and this is a vector. Since you have only one subscript, then this represents a vectorial notation. So rule number 3, the same free index must appear in every term of the expression. To make your mathematical expression valid and accurate, you must always follow these basic rules. And rule number 4, the number of free indices or index determines the order of the tensor. So the order of the tensor will now be a vector, and the order of a vector is of order 1. Okay, so I will discuss to you how to compute for the number of terms or elements considering the order of the tensor the next chapter. So I think I can stop at this point. We will continue some definition and some more rules and samples of tensors on the next video. So thank you very much for listening. Have a nice Dave.